If we map the Bitcoin mainnet as a physical geographic space, we can drop down into the structure of the blockchain to locate the exact origin point of an asset. Bypassing millions of other entries, we isolate block 923867. Deep within this specific block, we find the etching event for the NGF BTC AM rune, permanently recorded on the ledger by this transaction ID. This single transaction serves as the entry point for the entire asset registry, demonstrating how complex financial infrastructure can be anchored to a single unspent transaction output. The NESGESfinance project operates on a specific premise, tokenizing physical, real-world assets directly on the base layer of Bitcoin. Executing this exposes the project to immediate legal friction under frameworks like the Howey test in the US and MiCA in Europe. If developers attach direct economic rates, dividends, or yields to a Layer 1 token, regulators typically classify that token as an unregistered security. To navigate these specific regulatory hurdles, the system utilizes a dual asset architecture. Ensuring long-term compliance requires building a system where the rules are enforced at every level, from the macro legal entity structuring down to the byte-level serialization of the code. The etching transaction locked in the supply metrics permanently. There is a fixed supply of 5.93 billion tokens, with 100% pre-mine. The token was generated with exactly 0 decimals. This means it cannot be fractionally divided. Eliminating decimals enforces whole unit deterministic accounting. This is a requirement for institutional-grade proof-of-production audits. By locking these state constraints at inception, the supply cannot be inflated or manipulated. The protocol establishes a mathematically trustless baseline for the project. The defining rule of the architecture is that the NGF rune acts strictly as a non-economic utility key. It carries no financial weight. The actual economic rights and the governance structures for the special purpose vehicles are stored instead within a separate asset, an ordinal. A user must hold the utility key to access the contract, but the two assets operate in isolation. They do not share the same legal properties. This dual system is protected by a 3 of 5 multi-sig custody arrangement. Moving funds require simultaneous authorization from the asset issuer, an internal auditor, and an independent third-party partner. By mathematically severing the access key from the financial contract, the system insulates the heavily traded base rune from being targeted as a security. Moving past the economic model, we can inspect the compliance rules encoded directly into the NGF asset.json metadata layer. A human-readable asset registry is only a set of promises. The actual enforcement happens through a strict data schema using the JSON Draft 07 constraint engine. Autonomous pattern properties within the schema continuously scan allocation addresses and supply constraints, verifying compliance before any execution can occur. However, looking at the current state, the commitment_bytes field is explicitly flagged as pending. Until that commitment is cryptographically anchored, typically via an IPFS hash or a similar on-chain proof, the metadata lacks absolute immutability. This leaves a temporary trust gap in the architecture. High-level legal metadata is ineffective if the Rust implementation fails during a state transition. To handle data payloads safely, developers engineered custom Rust structural wrappers, specifically Bitcoin amount and Bitcoin outpoint. Native Bitcoin types cannot process serialization alone. Enveloping them in custom wrappers allows the system to apply Borsch serialize and SSS delegate traits. When Borsch serialize executes, it first writes a 32-byte array for the transaction ID, followed immediately by the output index as a 4-byte integer. Controlling this byte layout is the physical process of translating a regulatory framework into deterministic mathematics. To protect this memory allocation, the architecture relies on a defensive function, check script size. Its purpose is to enforce the max script size boundary on all Bitcoin scripts attempting to enter the system. If a script exceeds the byte limit, the system triggers a parse error script too large before any memory allocation is permitted. Terminating the process prior to allocation prevents the system from holding a malformed script. If an oversized script entered memory, it would eventually cause a panic during SSE encoding and corrupt the state tree. This chart maps the protocol architecture against inherent risks, balancing Layer 2 integration against AML compliance requirements. The data reveals a significant vulnerability: extreme supply concentration.
The entire 5.93 billion token allocation is currently held by only 11 addresses. Resolving this concentration safely will require executing KYC and AML routing at the SPV layer as the tokens are distributed to fund productive projects. The ngf.btc.am system demonstrates that tokenizing real-world assets on Bitcoin requires a coordinated architecture that bridges macroeconomic legal structures with byte-level memory safety.